Hello everybody, welcome to the homework helper for section 3.1. Let's go ahead and get started. In the first section, what we're going to be doing is completing inequality statements. Essentially what we're going to be doing is looking at these two columns and then trying to determine whether one is greater than, less than, equal to, greater than or equal to, etc. of whatever these are. So for example, if we know that A is larger than B, well, what's the comparison between having 3 A's and 3 B's? And for this one, clearly having 3 of a number that's larger is going to be greater than 3 of a number that's smaller. So we would say that would be greater than. Let's go ahead and move over. Let's look at like number 5. So the square root of some number that's greater than 10, or that number times itself. Well, square root means the number that when it multiplies by itself is that x. So that's going to be smaller than x, whereas a number times itself is definitely going to be larger, especially when we're talking about a number over 10. And then for a number between 0 and 1, this is my love zone. We're talking about some fractions here, okay? The fractions between 0 and 1. Well, what's going to be larger, that fraction or that number times itself? Think of it this way. We're looking at a fraction of a fraction, right? So that's going to be the smaller number than the number itself, right? A half versus a half of a half, right? Which would be a quarter. So no matter what that fraction is, when we're taking a fraction of a fraction, it's going to be smaller. So the original fraction is going to be bigger, okay? Let's go ahead to the next section where we're asked to be classifying functions. We want to identify the type, and the 3 types of functions that we want to be most aware of, or at least for this unit. For this unit, what we want to think about, linear, we want to think about exponential, and then we're learning about polynomial functions. And then these polynomial functions, the big one that you may have encountered before is quadratic. But we'll be looking to see if we can identify things that maybe are polynomials but not necessarily quadratic. But those are the big boys, linear, exponential, and then some polynomial. So when we look at this, number 10, we go 3, 6, 12, 24, 48. Now how is this growing? We can see that there's a consistent pattern of times 2, times 2, times 2, right? And whenever we're multiplying by the same number each time, that is going to be exponential. Right? Because in fact, the way that this would work is we would have, you know, our exponential equation is going to be y equals, you know, some starting value times our growth to the x power. Okay? Or in this case, we know that our growth is 2. We don't have our starting value. We have our first value, right? It's like, you know, our starting value is when you're born, but we have our first birthday, sort of a thing. So if this pattern were to continue, if we were going to go back a times 2, 1.5 would be our number, so it would be 3 halves times 2. So this is actually the equation of this. Times 2, x number of times. 1 times, 2 times, 3 times. So the fact that we have 2 to the x power tells us that it's exponential. Remember, exponential isn't just a function that has an exponent, it's where the variable is the exponent, right? For this one, the x is the exponent, and that's what's important for this. Okay, let's go to the next one. 3, 6, 9, 12, 15. We can see that each time we're adding 3, adding 3, adding 3. And when we add the same number each time, that's a linear equation, right? This is going to be y equals, you know, some ax plus b, where a is our slope or our growth rate. In this case, it's 3, so there's y equals 3x. B is our starting value. Again, we got to find our birthday, not, you know, or the day we were actually born, not our first birthday. If we were to go backwards, that'd be plus 0. So I don't need to write plus 0, so I just leave it like that. It doesn't ask you to write the equations, but I'm just kind of adding that so that we can see that. Okay, let's do this number 12, and then I'll let you do the rest on your own. We see it goes 3, 9, 18, 30, 45. Okay, so this is plus 6, but this is plus 9. Okay, so that's not working, as it's not going to be linear. This is times 3, but this is times 2. So it's not multiplying by the same number each time. So I know it's not exponential. So this has to be some polynomial. And in fact, when we look at the pattern, let's see what we're actually adding by. When we go from here to here, we're adding 6, 9, 12, 15. Okay, so we're adding in multiples of 3, right? 6, 9, 12, 15, 6, 9, 12, 15. So we're taking our growth itself is linear, right? So what this means is this is actually going to be a quadratic. When we have our growth rate that itself has a constant difference, right? Plus 3, plus 3. This is getting super messy. Here, let me go with the sticky note and kind of show this. When our growth rate has its own growth rate, that's linear. That's our clue that we're working with a quadratic. Because let's look at this. Let's look at our growth. So from here to here, this is plus 6. This is plus 9. This is plus 12, and this is plus 15. And then we're going to look at our secondary growth rate. Okay, so I'm going to look at what the growth rate of our growth rate. So growth rate sub 2, I'm going to call it. See, this goes plus 3, plus 3, plus 3. Okay, and so when our secondary growth rate, when our secondary growth rate is consistent like that, that's how we know we have a quadratic. And a quadratic, remember, is a polynomial function where we have some x squared. Okay, x squared plus whatever. But our quadratics have an x squared in it. Now be careful, because I see a lot of students confuse quadratics with exponentials because they both have exponents. But remember, when the variable is in the exponent, that's when it's exponential. But when it's an x squared, right? When it's an x squared, squared is a square, is a four-sided figure, is quadratic. Okay, let's go on to the next section. Oh yeah, long division. Who knew we would be coming back to long division? Now, these are kind of more basic long division problems to get you ready for a more complicated long division we're going to be doing later. But it's a good kind of reminder to recall how all of this means, or how all this works, excuse me. So for number 17, we're looking at 30 into 510. So the first thing that we do is we go digit by digit, okay? So I'm going to start with 5. Does 30 go into 5? No, 30 is bigger than 5. Okay, so now I'm going to go one digit over. Does 30 go into 51? I'm just going to kind of ignore that 0 for a second. Yes, 30 does go into 51. How many times? Once, right? Because we got 30 and then 60. And 60 is going to be too big. So goes in once, so 30. 51 minus 30. We then subtract this step. 51 minus 30 is going to give us 21. Okay. All right. So 30 doesn't go into 21, obviously. So we have to bring down our 0. Does 30 go into 210? Yeah, clearly. 30, 60, 90, 120, 150, 180, 210. Exactly 7 times. So that's 7 times to be 210 with no remainder. So I know my answer is 17. And then you're going to see it's going to ask you right here on number 19, is 30 a factor of 510? And how do you know? Well, we just did that problem in 17. Yeah, 30 is a factor of 510, right? 510, if 30 is a factor, 17 is a factor. How do we know that? We did it. Okay. These are going to be a little bit more complicated as we go down. Here's the deal. You can use a calculator to figure out how these if it does go into it, but I do want you to actually do the long division. Like, let's look at number 22 real fast, okay? When I look at number 22, 592, wow, that's a big number, right? Trying to figure that out in your head might be a challenge. I'm gonna do it just because I like challenges, but look at this. So 592 clearly doesn't go into 4, doesn't go into 40, doesn't go into 409, but it can go into 4,093. How many times does it go into 4,093? Well, I know the answer is 4 because 952 is almost 1,000. and then we're at 4,000, so I know it'll fit in at least four times, but I don't know what the remainder is going to be. So let me figure this out. So first thing I got to do is figure out, okay, what the heck is 4 times 952? I'll do this on a little scrap piece of paper here. So 952 times 4, that's 8, that's 20, that's 36, bring down the 2 is 38. Okay, so I know that this is 3,808, 3,808. Now I can subtract. Okay, that's going to be an 8, 13, 5, 8, borrow a 3, 10, 2, 285. Sweet. Getting closer. Okay, so now I need to bring down my 6. All right, now how many times does 952 go into 2,856? Well, if this fits just perfectly, it would be 3, but I'm actually not sure, so I'm gonna double check. So I got 952 plus 952 is 40. There's gonna be a 1 up there, 18, 19. Okay, now I'm gonna do 900, add another 952, because this is times 2, right? Let's see about times 3. So this is going to be 6, 5, 8, carry 2. Yep, perfectly, right? So it goes in exactly 3 times for 2,856. 0, boom, I got it, 43. Is it a factor? Absolutely. I know, is 952 a factor of this, of 40,936? Yeah, right? I know that 952 times 43 in fact equals that. Okay, so figuring out these factor trees is going to be important. Now, if you ever end up with a remainder on one of these problems, then whatever you're plugging in is not going to be a factor. So keep that in mind. The remainder means it's not a factor, it doesn't fit in perfectly. All right, best of luck on all of this, and I will see you in class.